a webinar series, Enlighten, and that series is actually concentrating about meeting with an interaction with industry professionals. So IEEE PES Kerala chapter and IEEE PES YP is jointly organizing this program to all the participants across the globe. So so today our guest was Mr. Pawan Penki. So he's an I just give a brief introduction of Pawan. Pawan is an experienced in very much experienced in power system protection engineer with over 8 years of experience in designing, developing, and commissioning in LV, MV, and SV production schemes. And he's a actually senior member, and he currently holds the lead protection and control engineer position in GE Grid Solutions. And before that, he worked as a protection engineer in Schweitzer Engineering Laboratories for 7 years, and he also served as a research assistant and teaching assistant at the University of Idaho, and under the guidance of Dr. Brian K. Johnson, his major professor. And Pawan holds a Master of Science degree in Electrical Engineering from the University of Idaho, and where he also earned an academic certificates in power system protection and amplifier relaying. Additionally, he holds a bachelor's degree in Electrical and Electronics Engineering from Geetha University of India, and currently is pursuing his PhD degree on his part-time basis at University of Idaho itself. And so I think his research efforts and the industry experience, we can utilize it and for this on our section. So you can write your queries in the chat box, and I will handle my mic to Pawan for the handling the session. Please, Pawan. Yeah, thank you.
Yeah, thank you, Rahul, for the wonderful introduction. I really appreciate your efforts in organizing this event. And good morning, everyone. Good afternoon, good evening, wherever you are. So my name is Pawan Penke. So I'm currently working as a lead protection and control engineer at GE Grid Solutions. So today's topic is about protection fault analysis methods using symmetrical components. So let's talk a little bit about our agenda today. So I'm going to talk a little bit about the introduction of the symmetrical components and the major power system faults, and the definition of the symmetrical components, their applications, where we use them, and some of the math behind how we would get these symmetrical components, and also how these symmetrical components behave during faults, and also corresponding network reduction techniques, and some of the field event analysis with followed by conclusion. Okay, moving on to introduction. So in 1918, Fortescue actually demonstrated that any set of n unbalanced phasors can always be expressed as sum of n symmetrical set of balanced phasors. And that became evident after in 1943, when Edith Clark actually gave a method of using these symmetrical components for three-phase systems, which are our majority of the power systems. So basically, the symmetrical component is a mathematical tool. It's purely a mathematical tool that simplifies the analysis of power system during unbalanced faults. So when I say unbalanced here, so let's see what a balanced three-phase system looks like. So in case of a balanced three-phase system, you have all three phases of equal magnitude and are all displaced by 120 degrees apart. So if you consider in North America, we have a ABC phase notation. And if you consider an ABC rotation, you have IA phase followed by IB phase and IC phase. And we also have a CB rotation, which is opposite phase rotation as the first one, which has the IA phase followed by IC phase and IB phase. Okay, so how does an unbalanced three-phase system look like? It can look like anything, any different drawing that is shown on this slide. So basically, the unbalanced three-phase system will not have equal magnitudes. They all will have different magnitudes on each phases, and also they could have different phase angles between them. So for our study purposes, this is very difficult to analyze the unbalanced three-phase system. In case of balanced three-phase system, you could always assume all the components onto a single phase. So that's how we do our single phase analysis. But in case of unbalanced system, you will not be able to like reduce all the components to a one phase, and it's not simple to do the analysis or do calculations with these unbalanced three-phase systems. So what causes these unbalanced three-phase systems? Power system faults. So our power system and a power grid is always susceptible to like different kinds of faults all through the day or all through all the seasons. So here are some of the major faults that are listed on this slide. So the major faults that are experienced by power system are single line to ground faults, line to line fault, line to line to ground fault, and a three line to ground fault. So among which the single line to ground faults are majority of the faults, which constitute up to 80% of the cases. So first three of these, SLG, LL, and LLG, they are all unbalanced faults. Three line to ground fault, when you have all three lines combined and together fall on the ground or touch the ground, it's a balanced fault. So some of the reasons why we get these faults is if you consider a single line to ground fault, one of the example is that a tree branch could always fall on a power line, which could be a temporary fault. So when you have a tree line falling on a power line, overhead power line, so you could have that tree line burnt within a few seconds and the fault will be clear. So that is the reason in case of some of these single line to ground faults, you also have reclosing enabled to let the power flow uninterruptedly. So some of these faults usually evolve into the line to line ground faults as well as line to line and line to ground fault as well. It always depends upon multiple factors, but these are some of the major faults that happen. So let's refresh ourselves with some basic concept of vector addition. So we all know that we all studied this concept in our early school, and if you want a particular vector, so vector is nothing but any component with a magnitude and a direction associated with it. So if you want a vector that is shown in the slide as C, you could always obtain this vector by adding two vectors that are shown on the figure, A and B. So if you add them, you will always get the third component, which is vector C. So here we could understand that a single vector could be decomposed into two different vectors and do addition among them. Likewise, in case of symmetrical components, all we are doing is we are splitting the unbalanced three-phase components into three sets and containing one set containing a positive sequence balanced component, another set containing a negative sequence balanced component, and followed by a zero sequence component. So the zero sequence component will always have three phases in series in phase with each other and are all equal magnitude. So from being unbalanced, we moved on to a balanced world where we have all our three components, three phases of these components are equal in magnitude and are displaced by 120 degrees. So the positive sequence will always have the same phase rotation as the original unbalanced system. So the negative sequence will have exactly the opposite phase as the positive sequence component. So as per Fortescue, this is what his definition is. Any unbalanced or any system with n phasors can always be split into equal number of balanced phasors. Okay. So we talked about these symmetrical components. So if we can talk a little bit about applications of the symmetrical components. So the symmetrical components can be used in the measurements. So in case of protection relays, these components help make decisions in real time. So the protection devices, protection relays that are protecting the power system, transmission lines, transformers, generators, or any component within the power system, they read the current and voltage values. They always make the live calculations within them and make decisions using these symmetrical components. And they are also used to save the event reports and records. And they are even also used in offline studies, like if you are designing, if you are at the design stage, or if you are at planning the setting stage. So they are all always useful. So they are also useful to determine your equipment ratings, stability calculations, and most importantly, some of the post-event analysis. When you have a protection event, you will always want to know why that happened so that you could rectify that and make sure that it never happens again in the power system. So these symmetrical components will help us understand what happened during an event and help us to solve that. Okay, let's talk a little about the math behind these components. So we explained in the previous slide that a single unbalanced phasor can be split into three different components. So here, as I showed in the previous slide, we have a positive sequence, negative sequence, and zero sequence components. So if we take IA phase can be split into three different components that are shown in this slide. IA zero sequence, IA positive sequence, and IA negative sequence. Likewise, exactly same for IB phase and IC phase. So as I mentioned before, here, all the IA0, IB0, IC0 are the zero sequence components. IB, IA positive, IB positive, and IC positive are the positive sequence components. And likewise, IA negative, IB negative, and IC negative are the negative sequence components. So among these, so we already know that the symmetrical components are balanced and equally displaced with each other. So if we know one particular component like A phase here, IA0, IA positive sequence, IA negative sequence, you could always get the B phase symmetrical components and C phase symmetrical components by multiplying these components with an operator which is defined as alpha. So alpha is nothing but 1 at an angle of 120 degrees. So did someone have any question? I think I hear some noise. Okay, let's move on. So here we have alpha, which is nothing but 1 at an angle of 120 degrees. So, and also by definition, we already told that zero sequence components are all equal in magnitude and are all in the same phase. So the zero sequence components will always be equal. So if we are trying to obtain, if we try to write the IB positive sequence component in terms of IA positive sequence components, we have to multiply that by alpha square. So we are rotating the phasor by exact same magnitude by 240 degrees in this case. And likewise, IC phase, we are rotating 120 degrees. Likewise for negative sequence components. So if you write all these equations in forms of matrix as shown in this figure, so you will get IA, IB, IC, which are the phasor components, summation of zero sequence components. As I said, all these three are equal. We write 1, 1, 1, 1, and we expressed the other components in terms of IA positive sequence. So we get 1 alpha square and alpha and a negative sequence component multiplied by 1 alpha and alpha square. If we further reduce this, we get a nice matrix that looks like this. So, and if you look at this equation, your phasor components are equal to this matrix multiplied by the symmetrical components. So if we define that matrix as A or a transformation matrix, so we can also rewrite that equation as the phasor components are equal to the transformation components times the symmetrical components. So our transformation matrix is helping us act like a bridge between these two worlds. So we can always go from um, phasor components to symmetrical components by applying A inverse, matrix inversion process here. So if you consider A inverse as one, and if you do an inverse of this matrix, you will get this particular equation that is shown in this figure. And the same operations can always be applied for voltages also. And these operations will always be applied for impedances as well. And many other applications are there for these matrix multiplications. So let's look at an example considering three phases that are shown here: IA, IB, and IC, 10 at an angle of 0, 10 at an angle of minus 120, 10 at an angle of 120. So if you want to calculate the symmetrical components for these phasor quantities, and we remember our previous equation where you apply inverse of the transformation matrix times the phasor quantities. So if we do that math here, you multiply the transformation matrix times the three phasor quantities, you get the equation that is shown here. So if you observe here, our system that is shown, example system that is shown, is actually a balanced system. So if you take a balanced system and apply the transformation matrix, all you're going to get is only the positive sequence component. So as I explained in the beginning of this slide, you'll only get the symmetrical components such as the negative sequence and zero sequence if you have an unbalance in the system. So if you do not have unbalance in the system, it's always the positive sequence is exactly equal to the phasor quantities. So you will only get only the positive sequence component. So that is evident with this equation. So this is a zero sequence, which is zero. This is a positive sequence, and this is a negative sequence. So likewise, if you do the same transformation considering an ACB rotation, you will always get only the negative sequence component as shown in the figure here. Okay, so how these symmetrical components behave during protection faults. So like I said, explained in the previous slides, that we have these four major types of the faults that occur in the power system. So we get these sequence components according to this table shown in this slide. So if you have a balanced three-phase fault, three-line to ground fault, you'll only receive a positive sequence from your calculations. You'll never have a negative or a zero sequence components. So if you experience an unbalanced fault, and such as a single line to ground fault, you will notice three different components, positive, negative, and zero, within your calculations. And if you have a line to line fault, you will have only positive and a negative sequence components. And if you have an unbalanced line to ground fault, you will have all three of these components. So let's quickly understand how these are shown up as in the table with a small example that is shown in this figure. So if you take a network shown in this slide with a generation source followed by a breaker and a transformer and a breaker, and followed by some transmission line and a breaker, distribution breakers as well. So if we write the equivalent network for this example system, so we're going to have a generation source and a source impedance or generator impedance as ZZ1 in the positive sequence component, a transformer positive sequence impedance as ZT1, and the line impedance as ZL1. So if you notice here, I only indicated the source in case of positive sequence components only. So that means that our positive sequence components are only driven by the source, and you will not never have a negative sequence or a zero sequence containing any sources here. So if you also notice that positive sequence and negative sequence are almost exactly the same, but except the source, that is true. And if you see the zero sequence components, there is a break in between these, if you notice this. So the reason for this break is that in case of a zero sequence components, if you notice here, our transformer is a delta and Y neutral grounded actually. So delta and Y neutral grounded transformer. So if you have a delta transformer on the primary, the delta winding of this transformer will trap all the zero sequence components. So for if a power system, if you need a power to flow, you need a closed path for any phase. So when you have all these three zero sequence components exactly in the co-phase all in nature, they all enter in the delta winding at the same point. And there is no way they will complete their path within the delta winding, and that's the reason they are all trapped and they circulate within the delta winding. And that's the reason that we are showing the representation here saying that the zero sequence components will not transfer from the delta to Y side. Okay, so talking about some of these key points, we mentioned that generators only produce the positive sequence voltage, and only positive sequence has a voltage source. And the positive and negative sequence diagrams for the transformers are exactly similar to those of transmission lines. And delta winding of the transformer, I mentioned that it traps all the zero sequence components. So if you want to start analyzing these unbalanced faults, so it all starts with developing these sequence networks in the beginning. So when you have a power system, the first job is to simplify the power system, write an equivalent network as shown in this previous slide. And when you start with this equivalent network, the next step would be your point of interest. So when you are trying to do some calculations for your fault current, your point of interest would always be at the fault location. So all you have to do is to create an equivalent network and a Thevenin equivalent of the entire network, looking from your fault location. So when you do that, you will be having an equivalent circuit for your analysis. So let's look at how we obtain these. So I mentioned that symmetrical. So in the case of a single line to ground faults, I mentioned that you have all three positive, negative, and zero sequence components. So let's look at this particular slide to understand how that particular statement is true. So if you take an example that is shown here with a fault in the location that is shown in this slide. So if we consider only the fault currents, okay, and we are ignoring the lower currents in this particular condition, if you just consider the fault currents, you will have, suppose if you have a phase to ground fault, so we only have a phase fault current, and you will never have any B or C phase fault currents. So if we plug in our equations to obtain our symmetrical components as the A inverse matrix, you will be getting these equations showing that positive sequence is equal to zero sequence, and that which is equal to the negative sequence. And let's look at the voltage condition in case of exactly the same single line to ground fault. So if you have the same single line to ground fault, if you have a fault resistance, you will have a voltage at the fault location as shown in the figure. If you don't have any fault resistance, the voltage will always be zero because the line is touching the ground. But Ideally, you will never have a system with a zero fault resistance. You will always have some fault resistance associated with any particular fault. So as you see in this figure, if you plug in the same equations, you will get that your fault location voltage is a summation of zero sequence, positive sequence, and negative sequence components. So if you look at the previous condition and this condition, so you have all these three components are equal together, and you have your fault location voltage is a summation of three positive, negative, and zero sequence components. So in order to satisfy these two conditions, your system need to be always connected in series. So in case of doing the sequence network reductions, your point of interest will always be at the fault location, like I mentioned, and you will be connecting the sequence network from your fault location point of view. So if you calculate the Thevenin equivalent of this system looking from the fault location, you will have Z equivalent, positive sequence, Z equivalent negative sequence, and zero sequence as shown in the figure. So our three networks are connected in series. So we have our I1, which is equal to I2, which is also equal to I0, which is flowing through 3RF. So there is a separate derivation how we get that three component with a fault resistance. I'm not showing that right now. So this is the way that you could connect your sequence networks in order to solve for your single line to ground fault current values. So when you connect these network in this fashion and you calculate all your I1, I2, I0 values, and then you can always apply your symmetrical component matrices to always obtain your phasor components. So that's how you do this thing. So likewise, if you also apply the boundary conditions that are shown in case of single line to ground fault, like here, um, you will have only IA phase. You will never have IB and IC phase. So likewise, if you apply the boundary conditions for line to line fault, so you will obtain the similar equations, which will lead you to connect these sequence components in the fashion shown here. So in case of a line to line fault, your positive and negative sequence components are connected in parallel together. And you will never have a zero sequence component. There is no ground involved with this. So your mathematical results will lead you to do this particular symmetrical network reduction. So likewise, if you have a line to ground fault, you will have all these positive, negative, and zero sequence components that are connected in parallel together with a fault resistance as shown here as 3RF. So likewise, for a three line to ground fault, so if you do those boundary conditions, again, you get only the positive sequence components. You'll never have a negative and a zero sequence components within them. So that's how you do these network reduction and do the calculations. So when we have a fault, our interest is to identify the fault current and also look at these three different sequence components to understand what kind of fault is that. So all these calculations happen in real time in production devices and make the decisions apparently and protect the system. So the motto of our protective devices is to identify the fault and clear the fault as soon as possible. So it identifies the fault by looking at all these calculations, and it sends a signal to the breaker and opens the breaker and clears the fault. So that's how our protective devices help in this. So let me share with you guys a quick event, field event. Let me share with you that, and we can talk a little about that. Okay, hope you can see my screen. So as you can see in this screen here, so I'm showing you an event, a protection event from a protective device, which is a SEL 710 device, which is a motor protection relay. So as you see this record, I'm going to show you quickly the voltages also for you to see how the voltages behave. So when you open the oscillography record of an event that happened in a relay, so when a protective device actually operates, so it's going to operate and it records the event that caused the protective device to operate in this fashion. So it saves some of the pre-fault condition, some duration of that, and it saves the faulted duration and also some post-fault duration as well. So all these records are saved within the protected device and they are downloaded and they can be used as I shown here for analysis purpose. So as you see here, you have three phases, IA, IB, and IC, which are shown in this particular first slot here. These are the currents. So these are the phasor currents that are recorded on the relay from the CTs of the motor. Motor has CTs and these CTs are connected to the device and they are measuring these values. So if you look at this, it's without doing any further analysis, it's hard to say what actually caused this particular trip and why they did the trip. So if you look at the voltages, also you will be hard to make decisions from this. So it's pretty much the devices are like if you consider a doctor, the doctor will be looking at all your electrocardiogram reports, blood tests, and all these to make analysis on you. Exactly the same fashion when we have the protection engineers, they look at actually the CTs and VTs, which are connected to the power system, which actually record some values. We look at these values to make decisions on what happened, how could it be prevented, or what is a problem with that. The only difference is that doctors have time, but engineers have only few milliseconds here, as shown in this figure, to make this call. So, as shown from this figure, you have voltages and currents. Let me minimize the voltages quickly. So if you see the second plot that I'm showing here, okay, let me also open the digitals actually. That shows you what actually happened during this. So we have this current disturbance. There are some phases that are increased, some phases that are reduced. And we have a trip that is being issued by the protective device. So the trip is issued at this particular time instance. Okay, so something caused this trip. We need to know what was caused this trip. So we have 50Q1T element. So 50Q1T element is the one that actually issued this particular trip. So what is 50Q1T? So actually, for people who don't know that, even this is a this elements are within the protective devices. So each manufacturer will name these elements as they want. And in order to understand these elements, we have to refer to the instruction, the operator's instruction manuals, the manufacturer's instruction manuals. So the 50Q1T is actually a negative sequence over current element. So 50Q indicates, 50 indicates over current element, Q indicates it's a negative sequence over current element. So 50Q1T actually picked up and it caused a trip, and which in turn tripped the breakers of the motor. So why the negative sequence? Let's look at what's happening with the sequence components. So I plotted here the I1 magnitude, which is the positive sequence current magnitude, I2 magnitude, and I0 magnitude. So if you see this plot, you only have a positive sequence and a negative sequence components. You don't have a zero sequence components. So from what we studied from the presentation, if you don't have a zero sequence components, there is no ground involved with this particular type of fault. So it's a no ground fault, So let's look further at what's happening here. So if you look at the positive and negative sequence components, they were actually so before the fault, you only have a positive sequence component in your system, and you never have the negative sequence component. It was very low or very close to zero. When this particular disturbance started, your negative sequence component that is shown in the green in color here actually shooted up. Okay, so when that particular component shooted up, so you have your 50Q1 set value. So our 50Q1 is actually set at, if you look at the protective device settings, you will see the 50Q is set at a value of 3. Okay, so when we have the negative sequence component I2 increased in this case, so our 50Q element is actually looking at the negative sequence component. So if you see 50Q1 value, which actually I calculated here, which is nothing but our negative sequence component divided by the CT ratio. So you get 3.41 here in this scenario, which is actually crossing our set value of 3. So that's when the timer actually started. So there is actually a delay associated with that 50Q element. So if you see the settings, you have a 100 millisecond delay, time delay associated with this. So once you have that element picked up and your delay timed out, you will have a 50Q1T timeout element issued. That's actually causing the trip. So what is this kind of fault where you don't have a zero sequence component and you have a negative sequence component that picked up very rapidly? It's nothing but a current imbalance fault. So these components actually help us make decisions within the relays and looking at the event records. And I wanted to show you, I couldn't find other records, but I wanted to show you 3 different, some of these records are not open, available for public, but yeah, so there are many other faults that could also be represented in this fashion. Okay, let me go back to my previous slide. Okay, now you can see my screen again. Okay, so coming to the conclusion here, so we proved that a three-phase unbalanced system can be broken down into 3 symmetrical components. The symmetrical components could always be transferred vice versa between the phasor domain and the sequence domain using our transformation matrix or inverse transformation matrix. And the negative and zero sequence components, which are present in the faults, actually prove that there is an unbalanced fault. So if you have a three-phase balanced system, three-phase balanced fault, you will never have a negative and a zero sequence. And if you talk strictly about it, you will never also have exactly balanced three-phase fault. You will have some imbalance within the power system with your loads itself. So with that case, you will never have an ideal three-phase fault. But if you talk about this theory behind it, if you have a perfectly balanced three-phase fault, you'll have a balanced currents flowing there, balanced fault currents flowing there. So with that, we proved that the symmetrical components have major applications in power system fault analysis. Thank you, and I'll take any few questions if you have.
Thank you, Pawan. There are a few questions in the chat box
Yeah, sure.
regarding. I will assist you. I will
Yeah,
For
sure.
real faults in power system, what does say zero sequence current are flowing in the transformer tertiary mean? I mean, the real faults in power system, what does the zero sequence current are flowing in a transformer tertiary means?
So in case of a transformer, so like I said, if you have a delta Y transformer, you don't have zero sequence components transferring from delta side to the Y side. But most of our power systems have your delta on your high side and Y on your low side, which are feeding the transmission lines or distribution networks from your Y side. So you have your Y with a neutral ground from your Y side or the low side of the transformer. So the reason that you have Y with a neutral ground is to allow your fault currents through flow through the neutral. It actually provides a closed path for the fault currents through flow to flow within the power system. So when you have a single underground fault, for example, so you will have so a fault can be at 100 kilometers or 20 kilometers, any location. So, but if you have a transformer at the substation, at the generation station, your neutral will have a current flowing through that. So the reason that is that there is a closed path that is provided by the earth, and your neutral is providing that closed path. And that allows your zero sequence components, which are nothing but the cofacial in nature, that are flowing through the transformer tertiary. When you say tertiary, it is pretty much, I assuming it is the neutral that is grounded. Okay, and maybe I can see the next question.
Yeah.
So I see the question, generally generators are able to feed the fault. Can transformer feed to fault? Um, that's nice. I mean, like I just explained that generators do feed the fault. Transformer are also feeding the fault when the generator is connected to it. So again, when you have a four-wire system, which is or a Y on the transformer secondary with a neutral grounded, that's where you would allow the ground currents through flow through the transformer neutral. Okay, so going to the next question. Is there any method to calculate distance to a fault point for open circuit faults? That's a very good question. So there are methods to identify the fault location. So when we talk about fault location, there are other techniques where you determine the fault location by. So if you know the distance protection is impedance-based protection. So with that technique, you will always be able to find the distance to a particular fault location. So when you have, there are other methods also recently which are known to the people that are traveling wave-based fault locations. So with these techniques, you will always be able to find the fault location to the transmission lines. Okay, just a second, next one. Is this method applicable to find the fault location in the transmission lines? Yes, these symmetrical components do help in making that decision, but like I said, there are multiple techniques to find the fault location. So the way that traveling wave fault locator finds out is that whenever you have a fault within the system, you have traveling waves that are generated from the fault inception. So those traveling waves travel either way to the two different ends of the transmission line. So we have currently the equipment that is available to record these disturbances and capture those traveling waves. So when we capture those traveling waves, we calculate the time that it took the wave to start from the fault point to the source, or the sending end or the receiving end. So when you know that these traveling waves are traveling at the speed of light, so you know the speed of light, and you know the total line distance, and you know the time when you received the traveling wave. So with these basic time and distance calculations, you will be able to identify your fault location. So those are some of the techniques that are available for us now. Okay. Another question is, can you tell which software are used in protective relays to analyze do you do the analysis of sequence components? So one of the software that I showed here is called SCL Synchro Wave Event Analyzer. I think if you register on the website, you will be able to download this using a trial version. You can do some of these basic operations that I have done. If you need a professional version, it could be purchased on their website as well. But there are other open source softwares also available, which are not on the top of my mind, but there are others as well. If you find on the web, you will be able to find some of those software. But the one that I showed is called SCL Synchrowave Event Analyzer. You can always search that and try to download it for your exercise. Okay, so another question is how the symmetrical components are used to detect faulted phases. So as explained in this presentation, we calculate, so whenever we have a fault, we do draw these. I mean, we don't usually always do these calculations. I just explained this to make you understand what's going in the behind the screens. So the relay will do the symmetrical component calculations. You'll always have the symmetrical components that are readily available for your analysis. Or you can always do your own math using MathCAD, MATLAB, or any other software. So when you have those values with you, based on the tables that I've shown you, you can always find what kind of faults actually happened by doing that calculations. Okay, another question is, for the distribution systems and microgrids, how to do fault analysis and circuit breaker tripping if grid codes are asking for fault right through? Okay, that's a good question as well. So right now, with the microgrids and also with the connection of all these IBR inverter-based resources, there is a requirement for the converter manufacturers to provide the fault current. So in case of conventional power system, you have synchronous machines sitting somewhere. Most of our systems were assumed in radial in nature. But with the microgrids and some of these new modern IBRs that are being integrated into the power system, you have power flow from multiple directions. So it's no longer radial, and you don't have strong sources that are feeding the faults. So the requirement here is that so when you have a strong source, you have enough fault current, you will have your protector relays set for those enough fault current, and you will be able to trip the relays. But when you have weak sources, like such as some of the distributed generation sources, so you don't have that enough strong sources. Um, in this case, some of these inverter manufacturers also have some of their like requirements to trip their system when the protection system has a fault. So the inverter manufacturers tend to protect their own equipment. So with that motive, they always, if they detect a fault, they trip their own inverter and go out of the network. But with that, we will never be able to identify where the fault is when the fault current is actually not present. Our protection elements will never operate and our device will never trip for that fault. So if you connect the inverter back again, you will always be closing onto inverter and you do the same and you'll never be clearing the fault. So in order to avoid this, we have some grid codes that are requiring these inverter manufacturers to provide fault current certain duration. So the the fault right through requirement here is that these inverter manufacturers should provide the fault current for a particular fault for a certain duration. So it's become a little challenge when we have these inverter based resources, when you don't have enough of the protection fault contribution from these devices. And you asked about how do you do fault analysis, and again exactly the same. So the basics of this fault analysis will never change even if you have a strong source or you have a distributed generation source. Our basics will still exactly hold true, and the same approach will exactly use even if you have a conventional source or a distributed generation source. Okay, another question we have here is how to distinguish between inrush current and other fault currents in transformer. That's a good question as well. So when you have a transformer that is being energized or starting, you always have inrush current that is drawn by the transformer. So it is important as a protection engineer to identify that the transformer is actually energizing and we should not be tripping for this particular condition. So our protection elements are tend to set above the load values, and when we have the current that is way above the load value, you always trip. But in this case, if you have an inrush current, your intention is not to trip for that case. So the way that we detect the inrush current is that by using some of the harmonic analysis. So when I say harmonic analysis, during inrush conditions, you always have second harmonics that are dominantly present in the power system. So the predictive devices will be monitoring these harmonics and they'll be doing internal calculations to extract these harmonics from these measurements from CTs and PTs. So they look at these the harmonic content, and based on that, if they detect the harmonic content, they say that yes, I have an inrush event going on, please don't trip. So it blocks the trip during that time frame and avoids the inrush current tripping. Okay, and another question is, are sequence components used in decision making in basic overcurrent and earth faults? Yes, absolutely. Um, so in case of phase faults, you always have phase components that are prominently present. When I say phase components, I mean if you have the positive sequence that are dominantly present. So when you have a earth fault, particularly when your fault has high fault resistance, you have low fault current, low phase fault current that is flowing. But when you have an earth fault, you always have high content of zero sequence components within your sequence component calculations. So these really help in case of earth faults. So if you have earth faults, your sequence components will really help. Particularly the zero sequence components will really help. So we will be setting the protective devices based upon these calculations beforehand. So you will do calculations assuming some phase faults in some simulation software, and you set your relays according to that. Your zero sequence component settings are always lower and sensitive because in your normal operation, in your balanced state, or in your regular conditions, you'll never have zero sequence components. There will be light unbalance within the power system because all three phases are not always equally loaded. But based upon those minimum sensitivities, you set your zero sequence component pickups. They are very helpful, they are fast. So they are really used in case of detecting ground faults quickly. Another question is, how does the proposed scheme differentiate fault from other disturbances? When you talk about proposed scheme, I'm not sure what you're mentioning there, but so when you have, okay, I need some clarity on what are those disturbances as well. If you could type in that, I would be happy to help with that. Maybe we'll move on to the next one. Okay, I'm not sure if my voice is clear now. Okay, so are the
It's
protection
fine. It's fine.
schemes, okay, sure. So are the protection schemes implemented for grid supply distribution systems used for islanded microgrids also? Grid supply distribution systems. So that's again a good question, Sandeep Kumar Das. So right now we have a great challenge here. So your protection, your microgrids are always connected to the power system. So when you have an islanding condition or islanded microgrid, you switch the microgrid, you open the point of interconnect, and you form a small like microgrid, and your microgrid is no longer connected to the grid. So when you have the grid that is connected to your local system, you have a strong source. But when you are islanded, you no longer connected to the strong sources. So in this case, protection has become a little challenging. I agree that, and there are some current studies that are being conducted in this aspect as well. So some of those are we actually have to detect the islanded condition in the local devices. It could always be based upon the point of interconnection breaker status, or there are other techniques that determine. If you use some controllers, they actually determine if the system is islanded or not. So when the system is islanded, um, there you could write some logic within your protected device to switch the protection set points to a much sensitive values. So when you have grid connected system, you have higher fault currents, and your uh, set one protection elements will operate, but the same elements will never operate when you have an islanded microgrid with a weaker source. So you have to switch those between those two using the detecting these islanded condition and use different sensitive protection elements. So there are some group switching activities that are also proposed. Some people don't prefer switching the groups. They do custom logics to detect island and use different protective or current elements for those. But it's an ongoing research and interesting topic as well. Okay, with that, I hope I answered most of your questions. If you still need any clarifications, do text here, or also you can always reach out to me. You can connect to me on LinkedIn, or you can ask any questions if you have. I can try to help you with any references that you need. And with with this presentation, like I mentioned earlier, most of my content I've taken from one of the book, which is Power System Analysis and Design by Duncan Sarma and Warby, and mainly from my coursework, actually, which I took long ago from Dr. Brian Johnson. He is a pioneer in power system protection. He teaches a course, actually, which is called EC 523, and which is which is actually provided by University of Idaho, where I actually graduated a few years ago. And also the event reports and also the software that I showed you, I actually acquired from CL website. And there is a webinar. You can, if you are interested in how to do those calculations, you can always go through that webinar, getting started with custom calculations using Syncrowave. There are other useful information as well in that website. You can always find that from there. That think we are right on time, and thank you very much. Anything
Yeah,
else, Rob?
yeah, we are extremely light on time. I think I will want to round up at the right time. Yeah. Thank you, Pawan. Actually, from IEEE Kerala chapter, and we are part of the IEEE OIP too. So it's a joint series. So yeah, thank you on behalf of IEEE Kerala chapter. I would like to thank you for the session, and it's a very basic, informative session. I think it is useful for all the. It was useful for all the participants here presented. So thank you once again, and thank you participants, and write it well your feedbacks and all. Thank you, Pawan. Bye bye.
Thank you very much, everyone. Thanks for joining. Have a nice day. Bye bye.
Have a
Thank you.
have a nice day, Pawan. Bye bye. Thank you.